I work with Ubitech along with my colleague Panagiotis. We will be presenting you several sessions on P4, and we will start gradually. First session is a very high-level introduction to P4, and then as we progress, we go into more technical details. So just a few words about us. We work with Ubitech. The group is Network Softwareization and IoT. And it's me and Panagiotis who will be giving sessions interchangeably. So before we start with P4, let's step back and see what SDN is about, actually, and how it started. SDN is about providing the ability of having packet processing pipelines which can be programmed outside of the device remotely through software. This kind of hardware devices which support pipeline-based programming, are typically ASICs, FPGAs, NPUs, or even CPU-based machines these days. And the question here is, what is a pipeline actually? We can see the pipeline as a set of tables which are traversed by packets in a sequence. And SDN is about providing the ability to actually program those pipelines, insert entries in those tables which tell dynamically how we modify packets as they go through the pipeline. Let's see how SDN began, actually. There's a sort of timeline here, which starts from 2008, roughly, when Nick McKeown et al. Actually introduced OpenFlow. It was, let's say, the early starter of SDN in 2008. In this paper, they described OpenFlow, and the first, let's say, one of the first SDN protocols out there. The idea about OpenFlow is that it provides a way to decouple hardware and software in networking and allow external controllers to program hardware devices, meaning programmable switches in this case, or routers, through entries which can be sent to those switches and be installed in their pipelines. In the first version of OpenFlow, we started with 1.0, a version which was supporting single table pipelines. So it was not actually a pipeline, it was just a single table. And there was only support for 12 fixed matched header fields. This means that the switch had a way, and it was burned in the hardware actually, to match very specific header fields in those tables. As we moved forward from 1.0 and onwards, we had advancements in OpenFlow protocol. Let's say up until 1.4 version, in which they introduced 41 fixed match header fields. So a lot of more protocols actually get support through OpenFlow. That had happened in August 23. However, at some point, P4 appeared. That was also around 2014, actually. And after that point, we had the discontinuation, let's say, of OpenFlow. There were no more versions released by the OpenFlow community. And the reason was actually the introduction of P4. And let's see why this happened, actually. As I said, in the specification of OpenFlow 1.4, we had support for 41 match header fields and 17 types of actions from the switches. The real problem here with OpenFlow was actually the fact that the hardware and the software were actually not in sync, let's say. They were not doing, when we release a hardware, let's say, to support OpenFlow, it can support certain types of match action operations. In some cases, we had switches which were not able to actually support all those 41 header fields that we find in 1.4 version, for example. This was because of hardware limitations. So there was a disconnection between hardware and software, essentially. The other aspect here is that hardware redesign requires long development cycles and increases the cost. So if we wanted to release a better switch, which was able to support those 41 header fields, we had to go through the entire pipeline of releasing new hardware, designing the chips, testing the chips, releasing the chips, which takes months, if not years. That was the reason, actually, that OpenFlow did not continue, and this is why P4 came into the landscape. So the real motivation around P4 was that instead of repetitively extending the OpenFlow standard to support more header fields, more protocols, more actions, and so on, why don't we define a new abstraction for programming the data plane without these kind of limitations? And how we could do that? So on the one hand side, P4 was a language itself. So it's a domain-specific language in which you can use to define the data plane behavior. And there is actually a compiler in P4 which allows you to describe the protocol headers that you would like to parse, or even invent your new headers, even for research purposes or future-proof experiments. Define the tables, define the actions and the counters and everything, and then apply this on either fast hardware like ASICs or FPGAs, or even software switches in the same way. The other aspect of P4 is that it also provides itself the interface to parse the packet, match on arbitrary header fields, and this way you can have, let's say, this coupling of hardware and software. P4 gives you the contract between control and data plane. So let's see together a concrete example of a P4 pipeline. This was called in the early definition the PISA pipeline, Protocol Independent Switch Architecture. It's actually the way we design P4-based switches to comply with the P4 standards. In the pipeline, initially, let's say in OpenFlow, we had only a set of tables like those that you see in the middle here. These are typical match action tables. They match packets, and upon a match, they just perform an action. In P4, we have two important extensions. It's a programmable parser at the beginning of the pipeline and a programmable deparser at the end of the pipeline. Let's see what this brings. Let's suppose that we write a new P4 program, which is, let's say, doing some layer 2 or layer 3 logic. And we write it in the P4 programming language. For this to be able to get into the switch, we need, first of all, to compile it, as I said earlier. This is a big difference with OpenFlow. So the P4 compiler here essentially compiles the code in the P4 program and generates the configuration of the parser dynamically. This means that it is able to understand what actual headers are important for this program to work. In this case, we have Ethernet, IPv4, IPv6, VLAN, UDP, TCP, and what are the interdependencies between those? So how you can create packets out of those different headers in an arbitrary way. So this way, we have a dynamic parser that you compile after your program. Then, let's suppose that we are able to start a P4-based controller, which will be using this program. Sorry for this. And we can run different sorts of applications on top of this controller, exploiting layer 2 and layer 3 principles. So we could have an application which does routing, let's say for IPv4, TCP, whatever, based packets, firewalling, and NAT, right? So through this controller, we will be able to create different tables in the pipeline. Each table could be used by a different application of the controller for its own purposes. So we can have, let's say, the gray table, which corresponds to firewall entries. This is the first logic we would like to insert in the pipeline. Then we do some NATing on the connections. And finally, we can do routing, let's say, to send the connection to some other entity in the network. So this way, when we have input packets traversing the switch, they first get into the parser. We identify what sort of packet this is. For example, it could be an Ethernet-based frame, which encapsulates IPv4 and then encapsulates a TCP segment, for example. This goes through the firewall, it goes through the NAT, and then an entry in the router and gets injected out of the pipeline. So this is how packets can traverse the whole pipeline of P4, starting from the parsers to identify what packet it is, and then based on this, see what entries actually correspond to this packet through the pipeline. By the way, feel free to interrupt me if you have any questions at any point. This ought to be an interactive session, most of all. So now, what is the difference in P4? Even in the days of OpenFlow, we still had ASICs. We also have ASICs today. What's the real difference here? Well, the reality is that the new custom ASICs that we have in the recent days offer very decent flexibility in hardware at very high speeds. So we have silicon chips which can do a lot more than we're capable of doing in the, let's say, 10 years or 15 years ago. And we have managed to increase also the throughput of those devices. At the same time, however, there is a lot of a blow up, let's say, in the silicon industry, which advanced a lot in the area of FPGAs. Sorry for this. There's this trend of smart NICs, if you have heard of it recently. So a lot of vendors out there construct smart NICs or switches out of FPGAs, specialized NPUs, like those by Netronome, for example, or even software-based initiatives like OVS and others, which try to offer a lot of flexibility in the hardware or in the software, which is even more flexible, at very high speeds. So P4 can take advantage of those and provide a lot more flexibility than OpenFlow could do. Now, we said about P4, we said how the pipeline looks like. However, we need some mechanism to actually program this pipeline at runtime. And P4, as I said, is a language for actually describing the behavior of a network element. We need a real-time API, which allows now a controller to connect to this device, see what's in the pipeline, and be able to send relevant entries in the tables of the pipeline. And this is what the P4 runtime does. It's the runtime aspect of P4. It's a protocol which allows to control P4-defined data planes. Let's see a quick comparison between P4 runtime and OpenFlow now. The key aspect of P4 runtime is actually the fact that it's protocol independent, which is not the case for OpenFlow. So in OpenFlow, we had achieved target independence because the same API works with different switches from different vendors. We had achieved pipeline independence, but protocol independence was not the case in OpenFlow. This is what P4 runtime aims to solve now, and it gives this independence all the way from target to pipeline to protocol. So we will see a lot about P4 runtime because this is actually the protocol that also the ETSI TerraFlow SDN controller uses to communicate with the switches. Before I close this introductory section, I will just show you quickly how we go from P4 code down to the, let's say, generated files of the compiler, of the P4 compiler, which get installed in the switch so as to be able to have a functional demo, so to say. So again, we start with a P4 program, which we write according to our needs. First step, as I said earlier, goes through the compiler. This is essential. And now, the compiler produces two kinds of outputs here. The first output is a P4 binary file. This is what actually gets installed into the target switch or device in general. So this binary here, according to the compiler, is actually target specific. It is coupled to the hardware. If we have an ASIC or an FPGA or even a software switch, a different binary will be produced out of this operation because it targets the specific hardware. However, on the other side, we have another output of the compiler, which is towards the northbound side, towards the controller side. And this is target independent. So it's actually the output of the compiler, which is called P4info, and it stands as a contract between the controller and the data plane. It's actually the schema of the pipeline described to the controller in a way that hides what type of device is underneath. So at this level, the controller does not care if we speak about an ASIC or an FPGA or a BMV2 switch. It uses an independent language to configure this device. And this is the key benefit of P4 with, versus OpenFlow here. It's exactly this target independence that we managed to achieve with this protocol. So in the coming sessions, we will see hands-on examples through this set of steps here, mainly focusing on software-based pipelines for the, let's say, for facilitating any kind of experimentation in this room. So the VM that you got already has a means to download Mininet, which has support for P4, and it actually starts BMV2 switches as independent switches in your topology. So this will be our focus. However, whatever we do today generalizes very easily to either types of targets here, including FPGAs or ASICs or whatever else. A set of references which we used to compile this initial slide set, just for you to know. And actually, I'm closing the session now. I don't know if you have any questions to ask. If not, the second session is about getting into ETSI TerraFlow SDN now to see what kind of abstractions it adds and how we can actually start using those different abstractions with a focus in P4. So let me switch the slides. Yeah, I'll do that. All right, so time to get into the controller of interest now, the ETSI TerraFlow SDN. So I will briefly show you the architecture that was also shared by Luis earlier. And then in this architecture, I will pinpoint to the specific elements that we care about today for this Hackfest, summarizing, let's say, the different abstraction levels that TerraFlow SDN offers today. Let's get directly into the slide set. So this is the architectural slide that you saw earlier. The set of microservices that we have already implemented in this TerraFlow ecosystem is on the top part of the figure. And let's say the bottom part of the figure is actually the infrastructure we attempt to manage. As you saw earlier, there is a bit of heterogeneity in the SBI part of TerraFlow, as we are capable of speaking different types of protocols here, like OpenConfig, ITF, ONF, P4, and so on. And as Luis said earlier, the whole environment of deploying TerraFlow is a Kubernetes-based environment, which comprises of multiple components corresponding to the different microservices. So for this talk today and for this Hackfest specifically, there will be three aspects of focus. The first set of components that we will be focusing is SBI on the TerraFlow side, which through P4 interacts with specific types of switches, specifically P4-based switches. And we will talk about the device-level abstractions of TerraFlow. In the second part of this talk, we will go into the service-level abstractions, so how service interacts with SBI to provide some higher-level abstractions. And finally, management layer abstractions through a policy component, which is able to bridge together service, SBI, but also the monitoring secretly here to provide some sort of SLAs. So let's get into the first level of abstractions, the device level abstractions. The focus here will be on the SBI microservice. I will start with a very simple example and start building upon this. So let's imagine that we have a simple topology of a single switch and two hosts connected to the switch. What the SBI component does, and I will specialize this SBI for this particular talk only on P4. However, as you saw earlier, we support a lot of more protocols here. So what this SBI does, actually, it has a way to handshake with any P4 device. So bring this device into the TerraFlow controller ecosystem, and then be able to configure this device through P4 runtime, the protocol that we use to configure P4 switches at runtime. How we do that? This SBI component has an API exposed, which allows the programmers to input some JSON-based configuration. So once we have connected with the device and we know that it's available on a certain IP address and port, gRPC port, we can send a JSON file to the controller, which looks like this. Let's see what this JSON looks like. Before I explain the JSON, the assumption here is that when the TerraFlow controller starts, it already injects a P4 program in the pipeline of the switch. So we assume here that this switch has already connected to the controller, and there is a P4 program that is installed already in the switch. So we know what kind of tables, let's say, this switch supports already. And we have a way now to manipulate those tables, to insert entries and, let's say, affect its runtime behavior. For this particular example, we assume some layer 2 tables are present in the switch, and we send a JSON file to, let's say, manipulate those entries. We start with the name of the table in the pipeline that we would like to affect through this rule. So we need to enter, as part of the JSON file, we need to enter the name of the table we would like to configure. In this case, it's the ingress pipeline implementation ACL table. ACL here stands for Access Control List. So it's a kind of a firewall-based table. Next, we described the set of match operations that we would like to perform on the incoming packets through this table. In this particular example, the header field of interest is actually the destination MAC, the destination MAC address of the packet, and we want to match a certain value. So all the packets that have a destination MAC address of this value actually will hit the table here. The third set of inputs here is basically, once we match a packet, what type of action we would like to perform. In this case, it's a simple action which says that we would like to clone this packet to the CPU. So send a copy of the file to the controller, essentially. We can also inject other information like priorities and stuff like that, which is optional in some cases. For this particular example, I will focus on the mandatory stuff. So this is the way to actually interact with the TerraFlow controller and ask him to insert an entry in a P4 switch. It's really a simple JSON file, and it's just 3 things you need to do. Pick the table you are interested in, define the match operation, define the action. Once you do that, the entry will be installed in the pipeline, and if a packet traverses the switches with this MAC address, a copy of it will be sent to the controller according to this action. This is the case. Now, it's pretty simple. Actually, if you have to manage just a single device, it's really handy. Managing one device is not a problem. The real problem here comes when we have more complex topologies, and especially when we have real networks. In this case, you need to manage a lot of those devices at the same time, and in some cases, some of those devices will not have the same tables as the others, right? So you cannot assume that every device will have the same P4 program installed. So the complexity of managing increasingly more and more devices is actually quite hard. So what we need for this, to overcome this problem, we need the necessary abstraction, which gets higher from this device layer. And this abstraction allows us to specify connectivity between some endpoints in the network. So let's say what we all know as intents, network intents here. Essentially, I would like to have connectivity between point A and point B, no matter what, no matter how many devices we have in between those points, I would like to get this connectivity done for me. Can the device layer support this request? No. No, because it doesn't know, from the SBI point of view, you don't know the entire network being set up. You just know the way to talk to a single device. You have the IP and the port of this device, and you have a way to send rules to that device. You don't know how many switches are in between those two endpoints, so you need a higher level of abstraction here to manage this. And this is how we get to service level abstractions. Is this clear so far, what we can do with the device level, right? This second part will focus on the service microservice of the ETSI TFS controller. And now we, let's say, elevate the level of abstraction. So what kind of abstraction we would like to introduce through this service layer? The first important abstraction is, as I said earlier, the ability of a user to define, to specify end-to-end connectivity intents between any endpoint in the network. This is very crucial. The second ability is, okay, we have already found point A and point B, and we would like to establish a connectivity. But how? There could be lots of paths between A and B in the network. I would also like to be able to select a path or ask the controller to select a path on my behalf with certain requirements. This is another important thing. Just merely establishing a connectivity between A and B sometimes is not enough. You might need to comply to certain, let's say, latency requirements, bandwidth requirements, number of hops, and so on. So you need also the ability to compute paths between endpoints. And this is another component in the service layer of Teraflow, which allows, through its interaction with service, to define two endpoints and compute a set of paths between these two endpoints so that you can pick any of those according to your needs. The third thing here is that despite all this luxury here, the ability to connect any endpoint in the network, you still want to be able to manipulate lots of different devices underneath. So you need this layer to hide the complexity of this A to B path establishment, let's say, of this intent-based networking, and yet be able to interact with SBI, configure each device with a set of desired rules so that you can get your connectivity established in the right way. So this layer appears to be really at a high level from the user side. It offers nice abstractions, but underneath it hides a lot of complexity, especially the way it interacts with the devices. So let's see an example here, how we could establish a service in Teraflow SDN. There's another JSON file for services, and through this JSON file, if we send it to the service component, we can create a new service. Among the other fields that are important here is the type of service. As Louis said earlier, we support certain types of services at the moment in Teraflow, including layer 2 VPN, layer 3 VPN, optical services with TAPI, and so on. So we can select a set of service types that we would like to support here. And of course, define the endpoint IDs. So where is host A in the network and where is host B in the network? Meaning, what is the device and what is the port of that device you would like to connect? As part of the service, we can also inject some constraints in the sense of service configuration rules, but this is out of discussion for now. Now, in this specific example, what we have as a JSON file here assumes a layer 2 service, a layer 2 VPN service, And we specify specific endpoints which correspond to the switches that you can see here marked with a yellow bubbles. So our connectivity service begins at switch number 1, P1, which is this particular endpoint, and terminates at switch number 5, P3. This is switch number 5, P3, right? So essentially, we would like to connect the two hosts of the topology through this intent. And here you can see how, if we expand actually this JSON object here, how it looks like internally. So for every endpoint, we define the device ID and the endpoint ID, meaning the port here. For this is endpoint A and this is endpoint B. Now, as I said earlier, choosing also some specific constraints for the service is an optional field which we can add in the configuration, but this is out of discussion for now. So what we achieved through the service layer, to summarize. Once we give those JSON files to the ETSI TerraFlow controller, we can establish a connectivity between A and B. And this is an end-to-end connectivity, right? So we achieve this end-to-end connectivity objective. And we, at the same time, to achieve this objective, the service component itself auto-translates this intent into a set of rules that propagates to the SBI component without the user knowing about it, so that the SBI can talk to the intermediate devices, send the correct rules, so that the path can be actually established, right? So this is what we have achieved. And another plus here, as I said earlier, is that sometimes we can pick a specific path through this connectivity intent. So we could choose either the north part to go from host A to host B, or the south part, depending on the number of hops, for example. The upper path has 4 hops, while the lower path has 3 hops, for example. So the service layer essentially hides this complexity of the device layer from the users and allows to define those connectivity intents. However, we have seen that how useful those service abstractions are, but as I said earlier, for real networks and for operators who operate on those networks, this is still not enough. Why it's not enough? Because sometimes network operators require means to trigger the service APIs, so how to create a service, how to update a service, or how to delete a service in an automated way based on some events that are coming from the network state. So you want to be able to monitor the network state, see what is down there, and based on some events, interact with the services dynamically. This is not possible in this service layer. And this is why we have management layer abstractions in TerraFlow as well. I will speak about one of them, which is related to policies, but there are others as well, like slicing and so on. So how we now jump from the service layer, how we can elevate higher. This is the topic. Before we do that, I said something specific previously. Operators want to capture the network state before they make any kind of decision to create a service, to update a service, or delete a service. How do we capture the network state is another discussion itself. And for this, there is a specific component in TerraFlow, which we call monitoring. And this is the component that actually interacts with the devices, collects the state of the devices and some important KPIs, maintains this, or persists more ideally, this information into a database which is available to other TerraFlow components, and exposes this information to other components so that they can use it. So I speak about monitoring at this point, although it's, let's say, a device level component, simply because for simply configuring a device, it's not important. But when we want to know the state of this device and make a decision based on this state, it's getting very important. So we enter the discussion about monitoring now because this is what the management layer of TerraFlow uses to make decisions. We need to know the state of the network to make a decision. So The bet now is, okay, we have found a way to capture the network state. This is through monitoring. Can we now exploit the synergy of what the service abstractions give us through service and path computation and the information that we capture here to do something more? Can we exploit this synergy? So the question is yes, and we can do that at least through the policy component. So what the policy component does here? As before, we can still create a new service the same way we did it before through the same JSON file. Now the service is up and running. We have connectivity between host A and host B. Oops, sorry. I messed up, sorry. So yes, through this JSON file, we establish the service. We have connectivity between endpoint 1 and 2. And now we can inject a policy. So we can create a service level agreement for this specific service. What this SLA does for the service. First of all, it has a one-to-one connection with the service itself. So the service ID that we created here is actually used by the policy. So we construct a new policy, a new SLA, which deals with this specific service. It is tailored to the service. And then what do? We need to provide another two pieces of information. The first is a condition on the service. Like, for example, when the throughput of this service goes below X kilobps or megabps, I want to know this. So this is the condition that something happens and is important for you to know about the service. We specify this through a set of JSON objects here, which we call condition list and a Boolean operator. If we have a lot of items in the condition list, so if I care about throughput and latency together, I can describe both throughput and latency in the condition list and also connect them through an AND Boolean operator, for example. And then, okay, when this happens, when the specific service, the throughput of the specific service goes below the predefined threshold, I get an event for this through the policy component. And I need to perform an action. This is what the policies do typically. So it's kind of an event condition action model. When the condition happens, I get the event and I apply an action. How this can be done, there is another field in the JSON file which we call action list. So some sort of mitigation action or remedy action that we perform from the controller down to the devices to be able to mitigate the issue or change the service in a way that now becomes better or tries to overcome any kind of problem, right? So how this works. When we create a new policy, we define the condition list here. Let's say throughput lower than X megabits per second. This tells the policy component that we need to register to monitor to the monitoring component and create a new alarm. This is what we call in monitoring. There is an alarm subsystem in monitoring which allows to define new alarms. So the policy asks for a new alarm. It says when for service X throughput goes below Y megabits per second, I would like to get an alarm. I would like to get a notification. This means that this event for me is important. So we register this alarm here. Monitoring establishes connections with the devices of this service. It starts monitoring the throughput of the service. And when this threshold is met for the throughput, it sends an alarm to the policy. It says, now your service has exceeded this throughput or this range. So this is done at this level down here, and the event is thrown back to the policy component when the alarm occurs. At this point, the policy needs to make an action. So the way we do the actions in general in the policy component is through interaction with a component which is relevant. For this specific example, we interact with the service because this is a service level policy. It was defined for this specific service. So what we do is we can trigger an update service call to the service component to change something in the service so that the throughput comes back to the normal, let's say, levels. So the policy component applies this update service action. Service and path computation, let's say, try to find some other path for the service to comply to the throughput requirements. They enforce this through the SBI. They enforce the new path in the service. So we have a new path now from A to B, so that hopefully the throughput now gets at the right levels. So what this whole workflow does is it creates a kind of a cascade set of events going from the management layer when we get this alarm about the service, down to the service layer to compute a new path for the service and change the service, and then down to the device level where we apply certain new configuration to the devices to change the service for the user. Is this clear? So through this last set of abstractions, let's say, of the management layer, we are able now to somehow close the loop between services which run on real devices, the state of those services, and what are the expectations of the operator for these services. So at the device level, we have seen the ability of TerraFlow to handle, let's say, or to accommodate different types of devices. We speak about before, but we support more types of devices here. So there is a heterogeneous data plane that we need to cover. And we need to be able to create device-specific and protocol-specific configuration for all these types of devices. This is the objective of device-level components. In the service-level components, we want to ensure end-to-end connectivity between hosts or between any kind of endpoints in the network. And this takes us from the level of a single device to the level of a whole service, of a whole network, actually. And of course, we offer path computation as a service here, which is important. And finally, at the level of management, with the support of monitoring here, as I said, which is a device-level asset, we are able to close the loop among devices, services, and the objectives of an operator, which are kind of, injected here as policies or SLAs. So through this policy framework, we can auto-update services upon specific conditions in the network. This actually finishes my second talk about the abstractions that we offer in TerraFlow today. Any questions, any comments? All right, hopefully this is clear. In the coming sessions, we get into the technical stuff now. And we will see, my colleague Panagiotis will now take you to a path of a complete P4 demo. So the steps you need to do to actually set up a working environment like this, more or less, not exactly the same, but similar, which includes all of these layers pretty much. It includes SBI component through the P4 runtime protocol, service component, specific end-to-end connectivity service here, and some policies on top to be able to manage the whole network. So thanks a lot, and I hope you enjoy the technical side of things now.